Good day, people of STEM-F. Today we will be discussing the Bronsted-Lowry acid and base. But before that, let's have this motivation that will give you an idea of what is Bronsted-Lowry acid and base. Here it is. Just as Bronsted-Lowry acids donate protons and bases accept them, true growth comes from giving and receiving. Embrace the exchange of ideas and energy to elevate your potential. Now let's start. The history of Bronsted-Lowry theory of acids and bases started in 1923, when the Danish chemist Johannes Bronsted and the English chemist Thomas Lowry independently proposed a more general definition of acids and bases. Their concept is based on the fact that acid-base reactions involve the transfer of hydrogen ions from one substance to another.
These slides explain the proton transfer reaction that occurs when hydrogen chloride dissolves in water. Hydrogen chloride acts as the acid because it donates protons, while water acts as the base because it accepts protons. The reaction can be represented as hydrogen chloride gas reacts with water to form chloride ions and hydronium ions. The hydronium ions is the key here, as it forms when water accepts protons. This shows the transfer of protons from the acids to the base, emphasizing the role of acid as proton donors and bases as the protons acceptors based on the Bronsted-Lowry definition. This is important because it highlights the behavior of the acids and bases in aqueous solution, which is fundamental in understanding chemical reactivity and pH.
The proton transfer reaction. This example explains a proton transfer reaction, specifically the reaction between hydrogen chloride and water. In the reaction that occurs when hydrogen chloride dissolves in water, the hydrogen molecule transfers an H positive ion, a proton, to a water molecule. Thus, we can represent the reaction as occurring between an HCl molecule and a water molecule to form hydronium chloride ions. Notice that the reaction involves a proton donor, which is an HCl, and a proton acceptor, H2O or water.
We have learned that acids are substances with a pH value lower than 7. We can test for acids by using universal indicator solution or paper, which turns red or orange depending on the strength of the acid. An example of an acid that you may be familiar with is hydrochloric acid. Hydrogen chloride dissolves in water to give hydrochloric acid. The only requirement for a Bronsted-Lowry base is to be able to accept protons.
The Bronsted-Lowry theory expanded our understanding of acid and bases beyond the older Arrhenius definition, which limited acid-base reaction to those involving the production of hydrogen ions and hydroxide ions in water. Bronsted-Lowry focuses on the transfer of a proton, a hydrogen atom that has lost its electron. An acid is defined as any substance can donate a proton, while a base is any substance can accept a proton. This proton transfer doesn't require a water-based solution. It can occur in a various solvents or even a gas phase. The reaction always involves a conjugate acid-base pair. When an acid donates a proton, it forms its conjugate base. And when base accepts a proton, it forms its conjugate acid.
So, you have now learned the concept of the Bronsted-Lowry acid and bases. For further understanding, take a look at this conjugate acid-base pair. Let's first define what conjugate means. Conjugate refers to the compound formed by the two or more chemical compound. Now, here's a more detailed breakdown of the concept for the Bronsted-Lowry acid and bases using the reaction between nitrous acid, which is the HNO2, and water H2O. Let's explore the forward reaction. We have nitrous acid and water as our reactants. We can see that HNO2 donates a proton to the water. And in this case, HNO2 is the Bronsted-Lowry acid because it donates the proton to the Bronsted-Lowry base that accepts the proton, which is the water H2O. When HNO2 donates a proton, it transforms into a nitrate ion NO2 negative, while water becomes hydronium ion H3O positive. The reaction can be summarized as HNO2 plus H2O yield into H3O positive plus NO2 negative. Now, let's look at the reverse reaction where we start with hydronium ion H3O positive and nitrate ion NO2 negative. In this case, H3O positive donates a proton to NO2 negative, in which H3O positive is the Bronsted-Lowry acid in this scenario because it donates a proton. Meanwhile, NO2 negative acts as the Bronsted-Lowry base since it accepts the proton. Now, this reaction will lead back to the forming of the HNO2 and water H2O. The reverse reaction can be summarized as H3O positive plus NO2 negative yield into HNO2 plus H2O.
In this reaction, we observe the concept of conjugate acid-base pairs based on the Bronsted-Lowry theory. Now, let's start with the forward reaction. HNO2 or nitrous acid donates a proton, which is a positively charged hydrogen, to water, which is H2O. By donating a proton, nitrous acid acts as the Bronsted-Lowry acid, while water, which accepts the proton, acts as the Bronsted-Lowry base. As a result of this proton transfer, HNO2 or nitrous acid becomes nitrite ion, which is its conjugate base. Meanwhile, water transforms into hydronium ion, which is its conjugate acid. Now, let's consider the reverse reaction. Here, hydronium ion donates a proton to nitrite ion. In this case, hydronium ion acts as the acid, while nitrite ion, which accepts the proton, serves as the base. This interplay demonstrates how acids and bases in one reaction convert into their conjugate in the reverse reaction. Essentially, when an acid like hydronium ion loses a proton, it forms a conjugate base, which is the nitrite ion. Similarly, when a base like hydronium ion gains a proton, this form conjugates acid, which is the hydronium ion. This irreversible process highlights the dynamic nature of acid-base pairs in chemical reactions.